Another situation related to capillary oncotic pressure is the infusion of saline versus the infusion of plasma or whole blood. Now, this is not explained in enough detail in the notes here, and it is important to understand the consequences of infusing saline versus plasma or whole blood. Now, the point here is, if you infuse saline, the dissolved substance is simply sodium chloride. And because sodium chloride penetrates a capillary membrane but not a cell membrane, when you infuse sodium chloride or saline, then that fluid will distribute in the entire extracellular compartment. Now, we said earlier that the extracellular compartment is 2/3 interstitial fluid and 1/3 vascular volume. Now, there's more to it than this, but the bottom line point is, if you infuse saline, most of that saline goes to the interstitial compartment. Because the interstitial compartment is larger than the vascular compartment, most of the saline ends up in the interstitium. Therefore, saline is a poor choice if you want to give a fluid to specifically expand the vascular compartment. Saline is a poor choice to expand mainly the vascular compartment because most of that saline ends up in the interstitium. On the other hand, if you're giving plasma or whole blood, that fluid contains plasma protein. And because plasma protein does not penetrate a capillary membrane, then most of that fluid stays in the vascular compartment. Giving plasma or whole blood is a good choice if you simply want to expand the vascular compartment. The fluid must have a dissolved substance that does not penetrate a capillary membrane for that fluid to remain in the vascular compartment. Another example could be dextran in saline. Now, the dextran molecule is a large molecule, and it, like protein, does not penetrate a capillary membrane. So if you give saline that contains dextran, that dextran will keep the fluid in the vascular compartment. So dextran in saline, then, is another good choice of a fluid to expand the vascular compartment. Now, like I said, all of those details are not in your handout, but they are important to understand then. Now, finally here, if we go to the last two variables, they're not nearly as important. Interstitial oncotic pressure. Now, this never goes down. It only increases. It increases if proteins accumulate in the interstitium. And this will occur specifically in chronic lymphatic blockage, not an acute blockage. The proteins will accumulate dramatically in chronic lymphatic blockage. And step one can talk about a tumor in the lymphatic system. If you have a chronic cancerous tumor in the lymphatic system, then it blocks the drainage. It blocks the drainage of the interstitial proteins. They will accumulate. They suck fluid into the interstitium, and that will promote peripheral edema. It is also possible that they could test situations in which you have greater capillary permeability. Now, what we're talking about here specifically is the protein permeability across the capillary membrane. So if you have situations where proteins are more permeable, such as in burns, then the proteins leak to the interstitium, they carry fluid with them, and that promotes peripheral edema. Now, interstitial hydrostatic pressure is not important except for respiratory distress syndrome on step one. And as I said, we explained the basics of this situation. We'll reiterate this when we get to respiration, so I won't dwell on this example at this point. Now that completes the first chapter in the peripheral circulation. I would now like to go on to Chapter 2. In Chapter 2 here, we're going to take a look at the regulation of blood flow and pressure. Now we're going to start off by looking at blood flow in both the systemic and pulmonary circuits. We'll look a little bit about pulmonary and then focus on systemic. Now the first aspect of this material is you can measure the blood flow through any organ or any tissue by using the Fick principle. So the Fick principle can be utilized to measure blood flow through any organ or tissue, but in step 1, they only apply the Fick principle to measure blood flow through the pulmonary circuit, and by measuring blood flow through the pulmonary circuit, you get an index of cardiac output. Now, I will go through the theory behind the Fick principle, but in step 1, all you have to be able to do is to pull the numbers out of a table and do a simple calculation. This is one calculation that is still consistently tested on step 1. Now, as I said, I will go through the theory of the Fick principle. Now, the Fick principle is simply you can measure the flow through any organ if that organ takes up a substance. The organ must take up a substance, and you have to be able to measure the uptake rate of that substance and the AV concentration difference. Now, we're going to apply this to the pulmonary circuit, and the substance we use is oxygen. Now, you have to be very careful when you're looking for the oxygen concentration in the blood in a particular compartment. Different units can be utilized to express this oxygen concentration. Now, for example, suppose we look at the pulmonary venous blood, which of course is the same as systemic arterial blood. The oxygen content of this blood can be expressed as 20 volumes percent. Now, 20 volumes percent is usually interpreted in terms of milliliters. So that means it is 20 volumes or milliliters per 100 volumes or milliliters of blood. So it is 20 mils of oxygen per 100 mils of blood. Now, whenever I do the calculation, I change everything to milliliters. And therefore, this becomes 0.2 mils of oxygen per mil of blood. So I change the units to mils of oxygen per mils of blood before I actually do the calculation. Now, this is really all you have to know for step 1. You simply have to be able to remember this equation, which calculates cardiac output or blood flow through the systemic circuit, and you have to be able to pull these numbers, these 3 numbers, from a table. Now, the numerator is the rate at which you take up oxygen, which is the body's oxygen consumption. Now, this figure here shows the oxygen consumption under resting conditions, and that is about 250 mils of oxygen per minute. So you simply plug the number in the numerator as 250, and you also write down the units, because units are important here. It's 250 mils per minute. Then the denominator is just the AV difference in oxygen concentration. You're looking for oxygen concentration, and therefore numbers about the PO2 in a compartment are meaningless. You don't need the hemoglobin concentration. You don't need the red blood cell count. All you need is the oxygen concentration. Now, what you do is you put the larger number first, which is the oxygen concentration in the pulmonary vein. Now, the oxygen concentration in the pulmonary vein is normally 0.2 mils of oxygen per mil of blood. But the point here is they may not give you pulmonary venous oxygen concentration. If they don't give you pulmonary venous oxygen concentration, you have to realize you need systemic arterial, because pulmonary venous and systemic arterial are basically the same number. So the first number here is either the oxygen concentration in the pulmonary venous system or the oxygen concentration in the systemic arterial. And under resting conditions, then, it would be close to 0.2 mils per mil of blood. Then you subtract the smaller oxygen concentration, and that would be the pulmonary arterial oxygen concentration. Now, under resting conditions, then, it's about 0.15 mils of oxygen per mil of blood. Now, again, if they don't give you pulmonary arterial, you have to realize you've got to look for systemic venous, because systemic venous is basically the same number as pulmonary arterial. And if you put 0.15 in them and you put down mils per mil, make sure everything is in milliliters, and if you do this calculation for a resting individual, it comes out to about 5,000 mils per minute. If I have to convert it to liters per minute, I do that after I've calculated in mils per minute then. So I do that final conversion. Now, as I said, this is a standard calculation that they still put on step 1. And the most likely reason they put this calculation on the exam is they expect you to know the pulmonary arterial blood composition. So they put it on the exam because they expect you to know the pulmonary arterial composition then is the same as systemic venous, and pulmonary venous composition is the same as systemic arterial. Now, what we want to focus on next is the regulation of blood flow at the organ level in the systemic circuit. So this material directly applies only to the systemic circuit. Once we finish the systemic circuit, we'll go on to look at the characteristics of the pulmonary circuit. Now again, we start off with a general statement here. Flow is regulated through the systemic circuit by constricting and dilating the smooth muscles surrounding the arterioles. Therefore, then, the regulation of blood flow to systemic organs is mainly via regulating the degree of constriction of the smooth muscles surrounding the arterioles. So we are looking specifically at the factors that regulate the constriction of the smooth muscle that surrounds the arterioles. Now, in systemic tissues, we divide them into two categories based upon the mechanisms that regulate the smooth muscles surrounding the arterioles. The first category represents tissues or organs that exhibit intrinsic regulation. Now, another common term here is autoregulation. Intrinsic regulation is the same as autoregulation. Now, in intrinsic or autoregulation, the mechanisms that regulate the smooth muscle are entirely within the organ itself. So all the mechanisms then that regulate the degree of constriction of the smooth muscle will be entirely within the organ itself. And the parameter that we're regulating is blood flow, not resistance. You have to realize the parameter that we're trying to regulate is blood flow. The tissue cares what the blood flow is. The tissue does not care what the resistance is. It is better to say we change the resistance in order to regulate the blood flow. So internally then, we are manipulating the resistance in order to provide an appropriate blood flow to that tissue. Now, because it is intrinsic or autoregulation, no nerves or circulating substances can be involved. That means that the autonomic nervous system, more specifically sympathetic neurons that release norepinephrine, are not involved in autoregulation. Circulating epinephrine has also nothing to do with autoregulation, because in both instances these represent messages coming from outside the tissue. Now, there are two theories to try and explain